All right, I'm going to go ahead and start section 7.5 here, which is a strategy for integration. And basically, now that we've looked at integration techniques, they're kind of they have a section where they kind of put all that together, and then you need to pick out which technique is appropriate to integrate the problem. Okay, as we've seen, integration is way more challenging than differentiation. So when you differentiate a function, it's pretty obvious which technique you need to use. When we integrate, it's sometimes not so obvious. So as I said, there's a collection of miscellaneous integrals in no particular order in this section, and the main idea is to recognize which technique to use. There's a summary at the beginning of the section, kind of just showing you various tips to consider. Also note that we cannot integrate all continuous functions. Okay. The following integrals are some examples of elementary functions that do not have elementary antiderivatives. This means that they are impossible to evaluate in terms of functions that we know. Okay, and it doesn't have to be some super complicated integrand. Like all these functions here that I've got written are impossible to do. There's no way to do them. Okay, doesn't that sound fun? So you might be doing an impossible problem. Okay, now there's in this section they're not going to give you an impossible problem. They're not going to be rude like that. But it is still worth saying that because of that, that's just another reason why integration is more difficult than differentiation. Okay. Now we have methods for approximating these types of integrals if they contain bounds. And these methods are in section 7.7. So 7.6 is really 7.5, but it's all in the calculator. In fact, the majority of elementary functions don't have elementary antiderivatives. So you can be assured, though, that all the integrals in this section are going to have elementary antiderivatives. Okay, so in other words, every single problem that they're giving you can be done. Okay. So I've just got some examples, really in no particular order here, and the idea again is to identify which technique you're supposed to use and then use the technique to get the answer. Okay. So what if we were going to integrate x squared times cosine of x dx? Okay. The technique that we would use would be integration by parts. Okay. And by the way, usually when you have a trig function times x to a power, it will usually involve integration by parts. Usually, not always. Okay. But that's one of the first things that I'm looking at, if I'm going to do the problem. So in this problem here, I'm going to let u be x squared and dv be cosine of x dx. I would not have those switched. Okay, because if dv is x squared dx, then v would be 1/3 x cubed, and that's not making the problem easier if I got a 1/3 x cubed, inside the new integral. Because I just increased the power by 1. So let's see. Under this system here, u is x squared, dv is cosine of x dx, du is 2x dx, and then v is sine x. Okay, so then u times v, that'd be x squared times sine x minus the integral for v du. 2 is a constant that can come out of the integral, and then times the antiderivative of x times sine x dx. Okay, again, don't forget your dx's and your plus c's there if you get an indefinite integral. Okay, and we just decrease the power by 1, right? And so maybe if we use parts again, we can get rid of x completely. So that's what I did here. If we let u be x and dv be sine x dx, du is dx, and v, the antiderivative of sine x, is negative cosine of x. Okay, so then let's see, I got x squared sine x, and then minus 2 times negative x cosine x. That's minus and negative means plus 2x cosine x. Okay, and then minus 2, I'm bringing in the 2 there, times the integral for v du. Okay, well, so I have the negative I can bring out there. So minus 2 times the antiderivative of cosine of x dx. Okay, and then I guess I can go to the answer now. Be x squared sine x plus 2x cosine x minus 2 times the antiderivative of cosine x is sine x, and then plus a constant. Okay, and go ahead and circle that. You know, and again, you know, just to emphasize this one more time, you know, be sure that you're simplifying as far as you can go here with all this stuff, okay? And leave the answers in exact form, okay? This next example, so what if we were going to integrate, it's a definite integral, we're going from 1 to 2, e to the 1 over x divided by x squared dx. Okay, well that would involve a u substitution. Okay, and by the way, just in a regular order here, just the first thing that I'm thinking of for any integral is, can I go to the answer? Okay, that'd be an easy problem, right? And then the next thing is, can I do the problem with just a u substitution? Now this other stuff that we've learned in chapter 7, that's a plan B option, right? So you know, if I can't do the problem with just a u substitution or go to the answer, then I'm looking at the form that it's in, okay? And that kind of tells me, you know, if I need integration by parts or partial fractions, or if there's some trig thing, or, you know, whatever, okay? Well, here, if I let u be 1 over x, then du, the derivative of x to the negative first power, that'd be negative 1 times x to the negative second power, or negative 1 over x squared dx. Okay, well, I've got a 1 over x squared dx in the integral, so I'll be able to knock out that part. And because this is a definite integral, remember, everything about my new integral has to involve the new variable, u. So I never want to mix u and x. That would be bad. That leads me to a wrong answer. Okay, so, well, these bounds here are in terms of x. Let's get in terms of u. If x is 1, u will be 1 over 1 is 1. Okay, so that's the lower bound there. And if x is 2, the upper bound, 1 over 2 is 1/2. So I'll be going from 1 to 1/2, integrating e to the u du. Now, from Calc 1, I've seen that, of course, when we have a definite integral, like the lower bound always needs to be the smaller number, the upper bound always needs to be the bigger number. I can go ahead and flip these bounds as long as I throw a negative in front of the integral. Well, I've already got a negative in front of the integral, right? So the opposite of a negative is positive, and now I'm integrating e to the u du, going from 1/2 to 1. Now, and that makes sense. Because now if I find the antiderivative, e to the u, plug in my bounds here, I get e to the first, then minus e to the 1/2, that's same as the square root of e, so e minus the square root of e, that would be the answer. Okay. Here's another one. So I'm integrating sine cubed of x times the square root of cosine of x dx. Well, that's obviously a trig integral, right? So I'd want to consider my identities and things like that. But this is going to be a problem coming from section 7.2. So if I pull away a sine x term, I'll have sine squared x times the square root of cosine x times sine x times dx, right? Sine squared x, that's the same as 1 minus cosine squared x. Okay, so if I get everything else in terms of cosines here and I get the sine x dx at the end, that allows me to then make a u substitution. Okay, if I let u be cosine of x, du is negative sine x dx. Okay, and so let's see, when I replace that, I'm going to have the negative I can bring out the outside of the integral. So I'm going to have negative the integral for 1 minus u squared times the square root of u, and then the sine x dx part can be replaced with du. Okay. When I distribute the square root of u into these two terms here, I got negative the integral for the square root of u minus u squared times u to the 1/2. Let's keep the base and add the powers. That'd be u to the 5/2 du. Okay, and then I can get the antiderivative then. So I'm going to have u to the 3/2 times 2/3, and the negative is going to come into that term, right? I'm replacing u. U is cosine x. So negative 2/3 cosine to the 3/2 of x plus, and negative times negative is positive, right? So be u to the 7/2 times 2/7. So I got 2/7 times u is cosine of x. So 2/7 times cosine to the 7/2 of x plus a constant at the end. That'd be the answer there. Okay, so we'd go ahead and circle that. Okay. Tell you what, why don't we go ahead and stop the video right there, and I'll pick up with this next example here in the next video.